This presentation considers the concept of resonance structures. Resonance structures are used to represent multiple equally valid Lewis structures of a molecule. The first example of the use of resonance structures is for the molecule ozone. Again, the structure is constructed following the 6 steps presented in the previous presentations. 1. Count all valence electrons possessed by the atoms of the molecule. 2. Determine the central atom based on the relative electronegativities. Here, since the 3 atoms have the same electronegativity, one will be treated as the central atom and the other 2 as terminal to it. 3. Create a skeletal structure by connecting each terminal atom to the central atom by 1 bonding electron pair each. Subtract the bonding electrons from the total. 4. Symmetrically distribute the remaining electrons as lone pairs to the terminal atoms until each terminal atom achieves an octet, or until the remaining electrons are all distributed, whichever comes first. Any remaining electrons are placed in pairs on the central atom, even if it causes the central atom to violate the octet rule. 5. Check the atoms in the molecule to determine if the octet rule is satisfied for each one. Here, the terminal oxygen atoms satisfy the octet rule. However, the central oxygen atom possesses only 2 bonding electron pairs and 1 lone electron pair, that is, 6 electrons. Thus, it does not satisfy the octet rule. 6. Create multiple bonds if needed to make the central atom satisfy the octet rule by changing a lone electron pair on a terminal atom into a bonding electron pair with the central atom. Then apply step 5 again to see if all atoms satisfy the octet rule. Here the terminal oxygen atoms satisfy the octet rule, and the central atom satisfies the octet rule. Step 7 does not apply. The structure seems complete, however both terminal atoms can interact with the central atom in the same way. An additional step is needed to demonstrate the equivalence of the central atom-terminal atom interactions. That step is 8. If the bonding between 2 or more terminal central atom interactions can be made equivalent by simply changing the locations of bonding and lone electron pairs, the appropriate resonance structure should be drawn. The resonance structures of ozone show the equivalence of the 2 possible configurations. The double arrow represents the equivalence of the 2 structures. Another example of resonance in Lewis structures is the molecule sulfur trioxide. 1. Count the valence electrons in the molecule. 2. Determine the central atom. 3. Set up the skeletal structure. Subtract the bonding electrons from the total. 4. Symmetrically distribute the remaining electrons as lone pairs to the terminal atoms. In this structure, there are no electrons remaining to place on the central atom. 5. Check for octets. The terminal oxygen atoms are satisfied. However, the central sulfur atom is electron deficient with only 3 bonding electron pairs, that is, 6 electrons. Form a double bond by changing a terminal atom lone electron pair into a bonding electron pair with the central atom. Applying step 5 again, the terminal oxygen atoms are all satisfied and the central sulfur atom is satisfied. Step 7 does not apply, so we continue with 8. This structure would be complete except that another equivalent structure can be made using a lone pair from a different oxygen atom. A third equivalent structure can also be made using the lone pair from the third oxygen atom. Double arrows are used to represent the equivalence of the 3 structures. The importance of resonance structures is that simple Lewis structures of molecules can misrepresent the molecular bonding characteristics. In ozone, there is not one single bond and one double bond. there's effectively an average 1.5 bond between the central oxygen atom and each terminal oxygen atom. Resonance structures are an addition to Lewis structures meant to convey such averaging. Resonance structures and molecules are commonly used in higher level chemistry courses to justify many molecular properties. The next presentation in this series will consider the use of formal charge to select the preferred form of molecules having inequivalent resonance structures.